The nickel-cadmium battery is a type of rechargeable battery using nickel oxide, hydroxide and metallic cadmium as electrodes. The abbreviation NiCad is derived from the chemical symbols of nickel and cadmium. The abbreviation NiCad is a registered trademark of SAFT Corporation, although this brand name is commonly used to describe all NiCad batteries. Wet-cell nickel-cadmium batteries were invented in 1898. Among rechargeable battery technologies, NiCad rapidly lost market share in the 1990s to NiMH and Li-ion batteries. Market share dropped by 80%. A NiCad battery has a terminal voltage during discharge of around 1.2 volts, which decreases little until nearly the end of discharge. NiCad batteries are made in a wide range of sizes and capacities, from portable sealed types interchangeable with carbon-zinc dry cells, to large ventilated cells used for standby power and motive power. Compared with other types of rechargeable cells, they offer good cycle life and performance at low temperatures with a fair capacity, but its significant advantage is the ability to deliver practically its full rated capacity at high discharge rates. However, the materials are more costly than that of the lead-acid battery, and the cells have high self-discharge rates. Sealed NiCad cells were at one time widely used in portable power tools, photography equipment, flashlights, emergency lighting, hobby RC, and portable electronic devices. The superior capacity of the nickel-metal hydride batteries, and more recently their lower cost, has largely supplanted their use. Further, the environmental impact of the disposal of the toxic metal cadmium has contributed considerably to the reduction in their use. Within the European Union, NiCad batteries can now only be supplied for replacement purposes or for certain types of new equipment such as medical devices. Larger ventilated wet-cell NiCad batteries are used in emergency lighting, standby power, and uninterruptible power supplies and other applications. History. The first NiCad battery was created by Valdemar Jungner of Sweden in 1899. At that time, the only direct competitor was the lead-acid battery, which was less physically and chemically robust. With minor improvements to the first prototypes, energy density rapidly increased to about half of that of primary batteries, and significantly greater than lead-acid batteries. Jungner experimented with substituting iron for the cadmium in varying quantities, but found the iron formulations to be wanting. Jungner's work was largely unknown in the United States. Thomas Edison patented a nickel or cobalt-cadmium battery in 1902, and adapted the battery design when he introduced the nickel-ion battery to the U.S. 2 years after Jungner had built one. In 1906, Jungner established a factory close to Oskarshamn, Sweden to produce flooded-design NiCad batteries. In 1932, active materials were deposited inside a porous nickel-plated electrode, and 15 years later began on a sealed nickel-cadmium battery. The first production in the United States began in 1946. Up to this point, the batteries were pocket type, constructed of nickel-plated steel pockets containing nickel and cadmium active materials. Around the middle of the 20th century, sintered plate NiCad batteries became increasingly popular, fusing nickel powder at a temperature well below its melting point using high pressures create sintered plates. The plates thus formed a highly porous, about 80% by volume. Positive and negative plates are produced by soaking the nickel plates in nickel and cadmium active materials, respectively. Sintered plates are usually much thinner than the pocket type, resulting in greater surface area per volume and higher currents. In general, the greater amount of reactive material surface area in a battery, the lower its internal resistance. Recent developments today, all consumer NiCad batteries use the Swiss roll, or jelly roll, configuration. This design incorporates several layers of positive and negative material rolled into a cylindrical shape. This design reduces internal resistance as there is a greater amount of electrode in contact with the active material in each cell. Characteristics: the maximum discharge rate for a NiCad battery varies by size. For a common AA size cell, the maximum discharge rate is approximately 1.8 amps. For a D size battery, the discharge rate can be as high as 3.5 amps. Model aircraft or boat builders often take much larger currents of up to 100 amps or so from specially constructed NiCad batteries, which are used to drive main motors. 5 to 6 minutes of model operation is easily achievable from quite small batteries, so a reasonably high power-to-weight figure is achieved, comparable to internal combustion motors, though of lesser duration. In this, however, they have been largely superseded by lithium polymer and lithium iron phosphate batteries, which can provide even higher energy densities. Voltage: NiCad cells have a nominal cell potential of 1.2 volts. This is lower than the 1.5 V of alkaline and zinc-carbon primary cells, and consequently they are not appropriate as a replacement in all applications. However, the 1.5 V of a primary alkaline cell refers to its initial, rather than average, voltage. Unlike alkaline and zinc-carbon primary cells, the NiCad cell's terminal voltage only changes a little as it discharges. Because many electronic devices are designed to work with primary cells that may discharge to as low as 0.90 to 1.0 V per cell, the relatively steady 1.2 V of a NiCad cell is enough to allow operation. Some would consider the near-constant voltage a drawback as it makes it difficult to detect when the battery charge is low. NiCad batteries used to replace 9V batteries usually only have 6 cells, for a terminal voltage of 7.2 volts, while most pocket radios will operate satisfactorily at this voltage. Some manufacturers such as Varta made 8.4-volt batteries with 7 cells for more critical applications. Charging: NiCad batteries can be charged at several different rates, depending on how the cell was manufactured. The charge rate is measured based on the percentage of the amp-hour capacity the battery is fed as a steady current over the duration of the charge. Regardless of the charge speed, more energy must be supplied to the battery than its actual capacity, to account for energy loss during charging, with faster chargers being more efficient. For example, an overnight charge might consist of supplying a current equals to 1/10 the ampere-hour rating for 14 to 16 hours, that is, a 100 mAh battery takes 10 mA for 14 hours, for a total of 140 mAh to charge at this rate. At the rapid charge rate, done at 100% of the rated capacity of the battery in 1 hour, the battery holds roughly 80% of the charge. So a 100 mAh battery takes 120 mAh to charge. Some specialized batteries can be charged in as little as 10 to 15 minutes at a 4C or 6C charge rate, but this is very uncommon. It also exponentially increases the risk of the cells overheating and venting due to an internal overpressure condition. The cell's rate of temperature rise is governed by its internal resistance and the square of the charging rate. At a 4C rate, the amount of heat generated in the cell is 16 times higher than the heat of the 1C rate. The downside to faster charging is the higher risk of overcharging, which can damage the battery, and the increased temperatures the cell has to endure. The safe temperature range when in use is between -20 degrees Celsius and 45 degrees Celsius. During charging, the battery temperature typically stays low, around the same as the ambient temperature. But as the battery nears full charge, the temperature will rise to 45 to 50 degrees Celsius. Some battery chargers detect this temperature increase to cut off charging and prevent overcharging. When not under load or charge, the NiCad battery will self-discharge approximately 10% per month at 20 degrees Celsius. ranging up to 20% per month at higher temperatures. It is possible to perform a trickle charge at current levels just high enough to offset this discharge rate, to keep a battery fully charged. However, if the battery is going to be stored unused for a long period of time, it should be discharged down to at most 40% of capacity, and stored in a cool, dry environment. Overcharging sealed NiCad cells consist of a pressure vessel that is supposed to contain any generation of oxygen and hydrogen gases until they can recombine back to water. Such generation typically occurs during rapid charge and discharge and exceedingly at overcharge condition. If the pressure exceeds the limit of the safety valve, water in the form of gas is lost. Since the vessel is designed to contain an exact amount of electrolyte, this loss will rapidly affect the capacity of the cell and its ability to receive and deliver current. To detect all conditions of overcharge demands great sophistication from the charging circuit, and a cheap charger will eventually damage even the best quality cells. Electrochemistry. A fully charged NiCad cell contains a nickel oxide hydroxide positive electrode plate, a cadmium negative electrode plate, a separator, and an alkaline electrolyte. NiCad batteries usually have the metal case with a sealing plate equipped with a self-sealing safety valve. The positive and negative electrode plates, isolated from each other by the separator, are rolled in a spiral shape inside the case. This is known as the jelly roll design and allows a NiCad cell to deliver a much higher maximum current than an equivalent size alkaline cell. Alkaline cells have a bobbin construction where the cell casing is filled with electrolyte and contains a graphite rod which acts as the positive electrode. As a relatively small area of the electrode is in contact with the electrolyte, the internal resistance for an equivalent-sized alkaline cell is higher, which limits the maximum current that can be delivered. The chemical reactions at the cadmium electrode during discharge are the reactions at the nickel oxide electrode are the net reaction during discharge is during recharge. The reactions go from right to left. The alkaline electrolyte is not consumed in this reaction, and therefore its specific gravity, unlike in lead-acid batteries, is not a guide to its state of charge. When Jungner built the first NiCad batteries, he used nickel oxide in the positive electrode, and iron and cadmium materials in the negative. It was not until later that pure cadmium metal and nickel hydroxide were used. Until about 1960, the chemical reaction was not completely understood. There were several speculations as to the reaction products. The debate was finally resolved by infrared spectroscopy, which revealed cadmium hydroxide and nickel hydroxide. Another historically important variation on the basic NiCad cell is the addition of lithium hydroxide to the potassium hydroxide electrolyte. This was believed to prolong the service life by making the cell more resistant to electrical abuse. The NiCad battery in its modern form is extremely resistant to electrical abuse anyway, so this practice has been discontinued. Vented cell batteries. Vented cell NiCad batteries are used when large capacities and high discharge rates are required. Traditional NiCad batteries are of the seal type, which means that charged gas is normally recombined and they release no gas unless severely overcharged or a fault develops. Unlike typical NiCad cells, which are sealed, vented cells have a vent or low-pressure release valve that releases any generated oxygen and hydrogen gases when overcharged or discharged rapidly. Since the battery is not a pressure vessel, it is safer, weighs less, and has a simpler and more economical structure. This also means the battery is not normally damaged by excessive rates of overcharge, discharge or even negative charge. They are used in aviation, rail and mass transit, backup power for telecoms, engine starting for backup turbines, etc. Using vented cell NiCad batteries results in reduction in size, weight and maintenance requirements over other types of batteries. Vented cell NiCad batteries have long lives and operate at extreme temperatures. A steel battery box contains the cells connected in series to gain the desired voltage. Cells are usually made of a light and durable polyamide, with multiple nickel-cadmium plates welded together for each electrode inside. A separator or liner made of silicone rubber acts as an insulator and a gas barrier between the electrodes. Cells are flooded with an electrolyte of 30% aqueous solution of potassium hydroxide. The top of the cell contains a space for excess electrolyte and a pressure release vent. Large nickel-plated copper studs and thick interconnecting links assure minimum effective series resistance for the battery. The venting of gases means that the battery is either being discharged at a high rate or recharged at a higher than nominal rate. This also means the electrolyte lost during venting must be periodically replaced through routine maintenance. Depending on the charge-discharge cycles and type of battery, this can mean a maintenance period of anything from a few months to a year. Vented cell voltage rises rapidly at the end of charge, allowing for very simple charger circuitry to be used. Typically, a battery is constant current charged at 1 ca rate until all the cells have reached at least 1.55 V. Another charge cycle follows at 0.1 ca rate, again until all cells have reached 1.55 V. The charge is finished with an equalizing or top-up charge, typically for not less than 4 hours at 0.1 ca rate. The purpose of the overcharge is to expel as much of the gases collected on the electrodes, hydrogen on the negative and oxygen on the positive, and some of these gases recombine to form water, which in turn will raise the electrolyte level to its highest level, after which it is safe to adjust the electrolyte levels. During the overcharge or top-up charge, the cell voltages will go beyond 1.6 V and then slowly start to drop. No cell should rise above 1.71 V or drop below 1.55 V. In an aircraft installation with a floating battery electrical system, the regulator voltage is set to charge the battery at constant potential charge. If this voltage is set too high, it will result in rapid electrolyte loss. A failed charge regulator may allow the charge voltage to rise well above this value, causing a massive overcharge with boiling over of the electrolyte. Applications: sealed NiCad cells may be used individually, or assembled into battery packs containing 2 or more cells. Small cells are used for portable electronics and toys, often using cells manufactured in the same sizes as primary cells. When NiCad batteries are substituted for primary cells, the lower terminal voltage in smaller ampere-hour capacity may reduce performances compared to primary cells. Miniature button cells are sometimes used in photographic equipment, handheld lamps, computer memory standby, toys, and novelties. Specialty NiCad batteries are used in cordless and wireless telephones, emergency lighting, and other applications. With a relatively low internal resistance, they can supply high surge currents. This makes them a favorable choice for remote-controlled electric model airplanes, boats, and cars, as well as cordless power tools and camera flash units. Larger flooded cells are used for aircraft starting batteries, electric vehicles, and standby power. Popularity: advances in battery manufacturing technologies throughout the second half of the 20th century have made batteries increasingly cheaper to produce. Battery-powered devices in general have increased in popularity. As of 2000, about 1.5 billion NiCad batteries were produced annually. Up until the mid-1990s, NiCad batteries had an overwhelming majority of the market share for rechargeable batteries in consumer electronics. At one point, NiCad batteries accounted for 8% of all portable secondary battery sales in the EU, and in the UK for 9.2% and in Switzerland for 1.3% of all portable battery sales. Now, in the EU and under the Battery Directive, sales of NiCad batteries to consumers for portable use has been greatly restricted. Availability. NiCad cells are available in the same sizes as alkaline batteries, from AA through D, as well as several multi-cell sizes, including the equivalent of a 9-volt battery. A fully charged single NiCad cell, under no load, carries a potential difference of between 1.25 and 1.35 volts, which stays relatively constant as the battery is discharged, since an alkaline battery near fully discharged may see its voltage drop to as low as 0.9 volts. NiCad cells and alkaline cells are typically interchangeable for most applications. In addition to single cells, batteries exist that contain up to 300 cells. This many cells are mostly used in automotive and heavy-duty industrial applications. For portable applications, the number of cells is normally below 18 cells. Industrial-sized flooded batteries are available with capacities ranging from 12.5 Ah up to several hundred Ah.